a talk by Professor Malcolm Longair, the impact of Maxwell's work on colour and statistical physics. Do you need any more setting up time?
5 seconds.
Right.
Which is done.
While he's doing that,
I'm set up.
you're set up.
Throughout his career, Maxwell worked simultaneously on so many different topics, and I've used the James Clerk Maxwell Foundation's website simply to give you here the dates of the various subjects that he worked in. This is by no means complete. Mathematical papers, electricity, magnetism, instruments, color, and so on. And here you can see they span the whole of his lifetime. Saturn's rings was only 3 years, and then he moved on to other things. But as we'll hear, a spectacular piece of work. And I've been asked to deal with these two slightly disparate topics, but all part of this extensive imagination that Maxwell has. Now, if you read Maxwell's papers, and I've been reading a lot of Maxwell's papers recently, you read in there a sparkle in the eye. There's always a slight little joke, a little twist in his writing. And so I'm going to give you a light and fun lecture, which I think that Maxwell would have approved of. At least, I'm certain he would have approved of. So we've got to deal with light first. Now, again, he was lucky that his father was very, very interested in all the new scientific toys, and in particular the optical toys, which were invented during the 1830s and 1820s and 1830s. And these all worked using the phenomenon of the persistence of vision, the fact that the eye has only got about a 20th of a second response time. Well, for examples of this is a splendid phenakistoscope, which was invented in 1832, where you look through a mirror through the little slats, and then you will see the people dancing. For example, like this. This is my PowerPoint version of the phenakistoscope. Right? You will see the lady and gentleman dancing. That's the looks of things. That was the precursor then of the zoetrope, which was invented a couple of years later. And here's an example of one of these beautiful zoetropes, which Maxwell had in his house, and in fact began drawing the various strips to go in it. Here's one of the later Maxwell zoetropes, in which, rather than slits, we've got concave lenses, which focus the image on the axis of the drum. And then you get a much sharper image, and you actually can enable more people see at one time. So it's, again, just typical Maxwellian ones. And then, typical of an academic, he then set this as an examination problem in 1866. We all do it. This is one of Maxwell's own hand-drawn zoetrope strips, which I've converted into a little PowerPoint, showing how the structure of a molecule. In that time, one had to find a way of making atoms in the continuous ether. And as Isabel Faulkner pointed out to me, the things that you could make were frictionless vortices, which could remain stable. And then this is an example of 3 atoms in a molecule. The clever thing is that Maxwell's only used 8 images to produce a 24-image cinefilm. And that's because of the threefold symmetry of it. It's very, very clever. Anyway, here is Maxwell, age 24. I've got to talk about color. And here he is, this famous picture of him with his color wheel here, which is also on the statue outside. Now, I've actually brought it along with me. It's been lost for a number of years in the Cavendish laboratory. We've been going into long-term store. And so here is the original Maxwell color wheel. And look, the colors have actually been preserved. It still can work. If you want to come up and touch it, you may pick up 1 or 2 molecules of Maxwell. I will leave it there. It's very precious. Anyway, that's what he used to study the the theory of light, which had been begun by Young. in the same great paper that we heard about earlier. And what Maxwell was interested in was quantifying exactly how much of the different primary lights you needed to be able to do that. And as I think is well known, by adjusting the amount of different colors on Maxwell's disk, he was able to produce diagrams like this, which tell you how much of red, green, and blue you need to add to get to this point here. And here are examples of these numbers. And also, this gave an explanation for color blindness. If one of the receptors for the red, green, and blue were missing, then you would have difficulty distinguishing the colors. And that, again, is the precursor of the tricolor diagram. This is Maxwell's original version with the red, blue, and green. And here it is slightly rotated, green, red, and blue, again, in exactly the same form. Now, that early work he was not satisfied with, and so while he was in Aberdeen, he got Smith and Ramage to build a spectacular light box. There's a replica of it in the James Clerk Maxwell's Foundation's building. And here it is here. We've got the original in Cambridge, and how it works is as follows. This is working it backwards. If you put white light through here, then it goes through these prisms, and it will split up into red, green, and blue lights. So what he did was to realize if you shine white light in this direction, then they will actually, you'll be selecting blue, they will come in that direction, red, green will come in that direction, red will come in that direction, and then by varying the width of the slits, you can get precise measurements of how much of each of the lights you need to add. So there it is, working backwards the way that Maxwell did it. And here it is from the Philosophical Transactions papers. Here is this is what allows different amounts of light through the different slits to appear at the eyepiece. And that's a fantastic piece of work. He tested many, many subjects and found indeed that the laws of color composition were the same for most people, except those with peculiar structures of the retina. And that's the precursor of the modern CIE diagrams, the Commission Internationale d'Éclairage. And here it is exactly the same. Here the saturated primary colors around the outside, and then you just add however much you are from each of these to make the colors in the middle. And here it is here. Now, just to show you that indeed this works, I brought along my own three-color system. So if we pop out the lights, all the lights, I will now turn up red. Right? That's red. I will now add green. Right? And now I will add in blue. And when we bring them all up to maximum, we should get something like white, except we don't, but there we are. You can't have everything. But what you can do is, to vary the amounts of each of the colors with this. Get rid of all the red again. You can see the way the different comes down. This is Maxwell's three-color system on a little machine. Thank you very much. Now, this story is going to carry on this afternoon when Peter Reid will give you a spectacular demonstration of what happened next. I am not going to queer his pitch by telling you what happens next. But do come along. That's it. Now, that's the first part of my talk. Now I'm going to do something completely different, which is to look at the statistical mechanics and thermodynamics. In the early 1950s, the two laws of thermodynamics were codified by Clausius and Thomson. Energy is conserved when heat is taken into account. No process is possible whose sole result is the transfer of heat from a colder to a hotter body. Now, Maxwell's research in demonstrating how the laws could be derived from kinetic theory was the work for which he was most well known during his lifetime. The work on electromagnetism and everything else were very much overshadowed by his huge contributions to statistical mechanics. Now, Clausius had already made very major advances in the whole notion of the kinetic theory of gases, and in 1857, working in terms of average speeds, he derived the famous gas law, PV equals 1/3 Nm U squared bar times equals RT. That's just the standard gas law. He knew there had to be a distribution of speeds, but he didn't know what it was. And that is where Maxwell's first huge contribution comes in. Now, in this 1860 paper, called Illustrations of Dynamical Theory of Gases, he derived the correct formula for the velocity distribution F of u, and then introduced statistical concepts into the kinetic theory of gases and thermodynamics. And that really is epochal, because now what you're doing is it's the beginning of a new epoch in physics, which was going to lead to the modern theory of statistical mechanics, as profound as anything that happened in the 19th century. Well, his derivation, which I've got on the next two slides, which I've blanked out because I don't want to scare people, but it's a fantastic derivation which takes literally 4 paragraphs. But what he did at the end was to derive this velocity distribution, which many people in the audience will recognize as the standard Maxwell velocity distribution. And it's interesting that at the end of that paper then he says, here are the important words, that the velocities are distributed among the particles according to the same law as the errors are distributed among the observations in the theory of the method of least squares. In other words, the statistics comes out of the analysis of what the equations have got to do, rather than putting in the statistics to begin with. So it's a very interesting way in which this occurs. This is introducing the fact that you have to get it. It comes out of the equations rather than it being put in to begin with. Now, this is where the fun starts. Now, I'm sure that Maxwell would approve of what I'm going to do. He loved models, all these mechanical models. His thought was really essentially mechanical all the way through. And when he actually developed the field ideas, he still couldn't quite get rid of the idea that there was mechanics involved behind it. But of course, he did that in the great 1865 paper. It is one of the utter great papers. As we said earlier, I had to review it, and I'd never really read it quite carefully, but it brings tears to one's eyes. This has got it all. It's absolutely wonderful. Anyway, Paul Alexander and I decided that the students didn't understand statistical mechanics and thermodynamics in the first year in Cambridge. And it was all, we said, look, let's do it all by simulation. So I'm going to show you some of the simulations we drive, which I love. And I regard them as being purely Maxwellian in spirit. I'm sure he would have loved it. So here's a simple example of where the Maxwell distribution comes from. We've got a box here where we put 5 quanta in these 100 squares there, just units of energy. And then here are the rules of the game. What we do is choose one cell at random and move one quantum to any other random cell. And repeat over and over and over again. That's all you do. Now, that's a completely symmetric process. There's no direction being selected to what's happening. We just simply do it. So here's what we did when in the first case. Here are, again, the 5 quanta. So we've got a total energy of 5 units, and that's they're all got the same energy. So now do that random process 100 times. Oh, it's beginning to look familiar, right? This is simply randomly redistributing single quanta. Then we do 200. Now, of course, you can't take anything from an empty box and put it anywhere. You've got to have, you cannot take anything out of an empty box and put it anywhere. And therefore, you begin to see things piling up at the origin because they've got nowhere to go. And then after 1,000 exchanges, it's beginning to look a wee bit more skewed, right? Like another distribution that we know very well. So now what we do is we now repeat with 10,000 cells, 20 quanta in each, and run it. Now, we do this live in front of the students, right? And I couldn't do that because it would take me an hour to do this lecture. So excuse me just showing you the four examples. After 300,000 exchanges, beginning to look familiar, all right? After 1.8 million exchanges, beginning to look familiar. And after 4 million random exchanges, what have we got? Well, we all know what we've got. We've got the Boltzmann distribution. It's a pure exponential. And we've done nothing. We've done nothing except play around with quanta. Now, in fact, the whole of statistical mechanics will be understood in this way. And what I'm going to say until the end is all about how you can do different clever things to illustrate what's going on. Now, what this doesn't show you is that picture is fluctuating like crazy all the time. right? It's fluctuating up and down, up and down, up and down all the time. And the students then saw that they might have a horrible derivation of the Boltzmann distribution, but they didn't see it wiggling about, you can be sure of that. Whereas this shows immediately that the key point about this is statistical equilibrium, where it's not one object that gets all the stuff all the time, it's constantly in motion and shifting around. And in fact, as I tell my students, all these bits up here, far away from where you started, that's the rule of biology. So that's where these very excessively energetic distributions come from. Again, the Boltzmann distribution is everywhere. It's in the whole of the Big Bang. Things using extremes on the distribution to do clever things, like reionizing the universe, like making helium and deuterium, like the interior of the sun, where it's all the 20 sigma high-energy particles that produce the energy, nuclear energy. And the whole of biology, the spermatozoa, which made all of us in this room, are still way out on the distribution. So we've got to thank Boltzmann for our existence. Now, having done that, he then could work out Falling Clauses, the ratio of specific heats, which again is a very simple calculation to do, and found the big problem that diatomic molecules such as oxygen and nitrogen give the wrong answer. And even when you put in all degrees of freedom, you never get the right answer. And in his great paper, he writes in the very final paragraph, finally, by establishing a necessary relationship between the motions of translation and rotation of all particles not spherical, we proved that a system of such particles could not possibly satisfy the known relation between the two specific heats of all gases. And there's this fabulous paper, and then says it's all wrong. Now, there was something funny was going on, but the guts of what was going there. Despite that, he was a strong adherent of the kinetic theory. It just was not quite clear how to get the correct ratio of the specific heat capacities. But one way of testing the theory was to use the transport properties of gases, in particular their viscosity. And here's the famous experiment, we've still got the original in the Cavendish, which he and his wife carried out to demonstrate that the viscosity is independent of the pressure, but it does not obey the expectation of kinetic theory, which is T to the half, but goes as T. And that was a very profound problem for Maxwell. Now, the consequences of this were, again, very profound. In 1857, he showed that if the collisions were not physical collisions between billiard balls, like that, but rather simply the effects of repulsive forces between fields, then if you adopted the repulsive forces going to r to the minus 5, then you find the dependence goes as t. Now, that is seriously profound. What he's done is to replace billiard balls by fields. Now, we always think of the great paper of 1865 as establishing fields, but here is another aspect where we're moving away from the mechanical world of Newton to the field world of Einstein. And it's not just electromagnetism. It's actually, you've thrown away the billiard balls and replaced them by points with a field associated with it. In the same year, 1857, Maxwell then, not too satisfied with the first derivation, because people, what the hell's going on in that simple piece of mathematics? He then solved the problem of random collisions between two particles and see what happens to the distribution if you do it. Well, given that challenge, Paul and I said, we'll do it too. But what would have happened if Maxwell had had a PC? I don't know. It's just unbelievable what he could have done. So what you do, first of all, is to solve the problem for the collision of two particles, in this case, equal masses. And the only unknown variable is the angle theta here in the center of momentum frame, and that's going to be random in random collisions. So you do exactly the same sort of thing we did before, but now we've got going to do 2 dimensions in the x and the y direction. So here is an array of momenta in the x and y directions, and we've just put in here an example where this is a flat distribution of total velocities we've got here. So here is the rules of the game. Now, another random set of boxes. Choose elements I and j at random, allow them to collide, and then choose the angle theta at random. Replace the old values of these by their new values, and then choose randomly the next pair of 7. Do it over and over and over and over and over again. Right? it's what Maxwell actually did in his beautiful paper in 1857, but we're doing it this way. So here's what happens. Now, I've just started off with more or less a square distribution of particle velocities in the two dimensions. And so now let's see what happens after only 1,000 collisions. It begins to grow tails, hardly surprisingly. After 25,000 collisions, where have we got to? Back to the Maxwell distribution again. And again, it's just a random sampling among the random collisions which produces this beautiful result. But you can do more than that. Suppose we now did the next simulation with different masses. One of mass m, another one of 4m. And now just go through exactly the same calculation again and see what happens to the two boxes. Well, there's where we start. After 10,000 collisions, we get it looking like this. And after 50,000 collisions, we get that. Right? Now, you can see exactly what you would expect. Well, if you're Maxwell, this is trivial, of course, but this is exactly what you might expect in the simulation. What we've got are two Gaussian distributions again, but now you will notice that this one has got with W, and this one's got with 2W, and that's the velocity dispersion. Right? Now, of course, the energy of the particle proportional to the square of the velocity dispersion, and so we've got half mv squared, the law of equipartition of energy being established through the collisions. So you've got so much happening in the one simulation of how it all came about and came together. I've said all of this already. This demonstration showed that you could derive the Maxwell distribution from the particle collision picture. Now then we come to the statistical nature of the second law of thermodynamics and Maxwell's famous demon. I think it's a most horrible, unfortunate, and unnecessary term, I'm bound to say, but it's one of these things that rolls off the tongue, and it's difficult to get rid of it. Anyway, it's no more than the idea that Maxwell said that, indeed, you can imagine taking the low-energy particles in this volume, passing them into this one and cooling it, and the high-energy particles in this one going to this one and heating it up, contrary to the second law of thermodynamics. And it's blindingly, obviously, correct. Now, of course, the name was probably introduced by William Thomson, although it appears in a letter from Tate, where Maxwell asked Tate, call him no more a demon, but a valve. And that's the correct expression. It's a hole. Maxwell's demon is a hole in the wall. So you can imagine we had to try to simulate that. And Maxwell, again, constantly emphasized it was designed to show the second law of thermodynamics as only a statistical certainty. Now, that ran completely in conflict with the views in the late 60s of Clausius and Boltzmann, who tried to derive the second law from purely the dynamical arguments. In other words, if you do these sorts of collisions I have and follow them, would it come out? And Maxwell made the point, absolutely impossible because Newton's laws of motion and Maxwell's equations are time symmetric. So you're not going to drive yourself to an equilibrium situation if you didn't start there. So that was, again, Maxwell's position. So, again, Paul and I had to do this too, right? This was to show to the students how the second law of thermodynamics comes about at the statistical level. So, here we've got now more of our lovely boxes. And the sad thing is we love doing this. We don't think the students necessarily understand a bloody thing. But we loved it because we could say, my goodness, this is the way to do thermodynamics and statistical mechanics. So again, here we've got two isolated boxes. So here's, again, our array of 500 quanta, and now after a certain time we get to this situation here, where we're just by doing the swapping of quanta around, and we've done the same now with the second box, which has only got two per cell, so this one's clearly much hotter than that one there. Right? And if we just run them separately, then the two grids will tend to Boltzmann distributions with different exponents. So here is us repeating it with much bigger grids with 20 quanta, another small one with 5 quanta, and they end up with these distributions where you can see very, very clearly that they've got different exponents, beta. Beta and alpha are going to end up being inversely proportional to temperature in the system, but there they are like that. But now all you do to actually put the Maxwell demons in, the Maxwell holes in, is you now allow the particles not just to select themselves randomly from here, but from there and there. And it's entirely random. It's purely statistics. You just have the same rules, but now you're allowed to select from bigger phase space, if you like to put it that way, the particles. So here we are here. This is what's happened in this case. Here's what's happened in this case. And what's happened is the following. We started off with 500 quanta in this one here, and then by random processes, this has come down to 484 quanta. This one here has started with 50, has gone up to 66 quanta. But it's entirely random. We're not telling it to go in any particular direction. It's just pure exchange of individual quanta between the boxes. And when you look at it, here it is. Here are the distributions here. There is the distributions now for the much bigger sample that we've got here. And you can say they've ended up with exactly the same values of alpha, just different amplitudes because we've got different number of quanta in the box. So there they are there. And of course, they're fluctuating all the time. And of course, Maxwell's point was that if you look at this simulation, every time a quantum moves from that box to that box, it's violating the second law of thermodynamics. And it happens all the time, all the time, all the time, all the time, except there's a vastly greater probability they're going to go in the right direction. So it's wonderful, wonderful, wonderful stuff. Right. Well, that's all I wanted to say. The work is absolutely staggering of Maxwell in this region, and if only if people could really appreciate just the sheer genius of himself. I put these pictures up because these are the famous pictures that we've got in the Cavendish of Maxwell and Maxwell with his wife. We've had the Hamilton Carr Institute go and work on them, so they've cleaned them all up. I'll be sending copies to the James Clerk Maxwell Foundation of the new refurbished things. And they're absolutely fabulous pictures. They've also taken X-rays and infrared images of that, and we now know that this was overpainted. There's a tree here that's been disappeared. But even more spectacularly, this picture here is an overpainting of the photograph of Maxwell, which he had taken when I think he ascended to the chair. Now, do I have 1 minute to show the picture? This might stagger people, okay? I didn't put it in because I thought I would run out of time, but if I take you this picture here, and I bring it up, this picture here is an overpainting by Jemima of that picture. That picture is underneath there. And you can see there's the bit of the coat there, there's the bit of the coat there, there's that bit of there, and you can just see it very faintly on it's there. And look what she's done. She's converted him from a grizzled older statesman into a Byronic romantic hero with black hair, with rather luscious lips. Read what you like into this. But we will be writing up this, Isabel Faulkner and I and the people at the Cavendish Institute. But when you look at this picture, this really is my vision of him as the romantic hero, the person who did all these imaginative flights of the imagination to produce modern physics as we know it. Thank you very much.
Very much, Malcolm. You better take a few questions.
Of course, with pleasure, yes.
Right. Questions, comments? Yes, please, here in a blue shirt.
I'm sorry, it's a very trivial question. But Maxwell's statue out there has a lovely little dog, which is destined to become the second most famous sculpted dog of Edinburgh. Yes. And the dog appeared in the photograph that you just showed with his wife. And I know that he used the dog for generating electrostatic experiments in his laboratory. He was obviously very fond of his dog. Do we know what the dog was called?
Yes. Now, there are very few things for which I will claim credit in life. But I will claim credit for the dog on the statue. Because when we were discussing it with the sculptor Sandy Stoddart, I said, you must get the dog. And he was delighted because he then said, yes, that fills up that bit underneath there. And so he took one of Maxwell's many dogs. He had many different dogs. They were all called Toby, T-O-B-I. So one Toby was replaced by the next Toby. And also, Toby went round the laboratory with him every day, talking with the students. So, you know, dogs and this, I forget the term that Sandy used. It was human-animal sympathy, or words like this, was very much a part of Maxwell's life.
And this is the thing that he's holding in the statue?
That's exactly what he's holding in the statue.
Yep.
Yes.
Thank you.
Is Michael there?
Michael, in the front, please.
Your description of Maxwell's work was brilliant, and I certainly enjoyed it. But that was all before the development of quantum mechanics. What would Maxwell have made of quantum theory?
I would not go that direction, I've got to say. I think the important contributions are from Boltzmann, because Boltzmann then used all of Maxwell's works in order to then create the proper statistical mechanics. And the integral part of Boltzmann procedure is to start with quanta. Right? So the way that you got to read through the story from Boltzmann then to Planck, and Planck then used badly the work of Boltzmann in order to get the Planck distribution. So the quanta come from essentially my simulations, right? But now with the extra quantum layer added on top. So I believe that my simple answer is Maxwell didn't need the prop of a simulation to do what he did. He was able to do it just because he knew what he was doing. That's right.
Time for one more question or comment. Yes.
I was wondering whether or not we should remark that Boltzmann was not recognized for his work in his time, to mention again a point that Michael made earlier. Was a young scientist whose work was deemed not important enough to publish. And just a second thought, how close was Maxwell to discovering the Boltzmann theory, in the sense that Boltzmann derived or identified his distribution knowing the Boyle's law, essentially, that by necessity implied the Boltzmann distribution?
Well, there's no question about the fact that Boltzmann knew the Maxwell papers backwards, so that he would be very familiar with all of that. But again, he was taking a very different, much more general approach, the same as Gibbs and others are going to do later, to actually nail down the theory. You're absolutely right. You see, the problem was that the kinetic theory was always slightly suspect because it couldn't get the ratio of specific heat capacities right. And so that's why the energeticists through the last part of the 19th century could still say, kinetic theory is molecules don't exist. You're simply it's an unnecessary artifact. But Boltzmann's work, of course, and he was in Central Europe, in Vienna and Goetz and places like that, in the midst of all of these arguments about whether the reality of molecules exists. So again, you're right. He was not fully appreciated. We appreciate him now.
I think we'll have to stop at that point. Thank you very much indeed, Malcolm.
Thank
for
you.
a superb lecture.